Hello, everyone. Thank you for coming to our second day's International Cloud Modeling Workshop discussion. And it was nice to see so many friends yesterday. And sorry about the technical difficulties. And today, our IITM colleagues helped to set up a YouTube link that for those who just want to watch and listen to the discussion can use that link. And for those who want to actively participate to the discussions, and welcome to join the room. So today will be our second day discussion on the single congestus cloud, and our case leaders are Shinichiro Shima and Wojciech Grubowski. We'll give the stage to Shinichiro to run our meeting today. Before we start, any updates from Sandeep or Harish? Do you want to chime in for any items that we need to pay attention to? Okay, if no,
Hi,
yeah,
Lulin.
Sandeep, go ahead.
So I hope you're aware about the new room that we have set up with a YouTube link. Okay,
Yeah,
so fine.
and we received the emails. Yeah.
Yes.
So if you
so
can,
that. Yeah,
go ahead.
please.
I
Please
mean,
go ahead.
if you can put that link somewhere in the meeting room or somewhere that people know.
If you look at the chat box, I have pinned some announcement on the top. So the link is given on the last line. So if someone wants to copy paste into their browser, they can watch the YouTube.
Okay, I see. Thank you.
Yeah.
In the chat. Thanks. Very
yes,
good.
There is an announcement. Yeah. Okay.
Great. Thank you very much. And without further ado, Shinichiro, why don't you take over and get our second day started? Thank you.
Thank you. Let's start. So, Wojtek, I think we are supposed to go to the stage. Wojtek, you are muted. You're muted. Okay, just a test. This is just a test, in case you have something to say.
Okay, I mute myself, so you will be talking, so that's fine.
Yes,
good morning, good afternoon, good evening to everybody, and I mute myself.
Okay, then let's start. So, my name is Shinichiro Shima from University of Hyogo. Thank you everyone for joining us today. I would like to also thank Lulin, Shivsai, Tara, and all the organizing committee for your effort to make this meeting possible under this very difficult situation. So let me share the screen. Can you see my screen?
Yes.
Okay. This is today's agenda. So I first overview the case description very quickly, and then reports from all the groups follow. And after that, we will have a discussion. Then to the poster session. Okay. So now I explain our case very quickly. So wait a moment. Okay. Can you see my slide? Oh, great. So this is a cumulus congestus case, and The setup is almost the same as Lashutra et al. 2005. And this is based on scams field campaign. More detail about the case description is provided from this link. You can find it from the website as well. So this is the objectives of our MIP, Model Intercomparison Project. The key objective is to compare beam models and particle-based cloud microphysics model and a realistic turbulent flow of a cumulus isolated single cumulus congestus cloud. So the key questions are as follows. Is the broadening of droplet size distribution due to turbulence well captured? Is the surface precipitation consistent between the two types of microphysics, detailed cloud microphysics models? Any impact of numerical diffusion of beam schemes and the computational cost of the two schemes? This is a list of participants. So CM1 is led by Kamal Chandrakar from NCAR, and OILAG is led by Wojtek Grabowski, and Scale Beam by Yosuke Sato from Hokkaido University, Scale STM by me from University of Hyogo, and UW-LCM by Piotr Ojikan, University of Warsaw, and WRF-UPNB by Kyung-Ok Choi from University of Washington, and finally WRF-UPNB by Lulin Shiure from NCAR. And the color represents a type of model, microphysics model. CM1 and OILAG has both types of microphysics schemes. And as I showed you, this is today's agenda. And let me explain the case description briefly. So this is the initial sounding. This is provided by Professor Sonia Lashutra. And it's from the scams field campaign. The cloud base is around 1 kilometer here. Okay, let me turn off the laser pointer. Yes. 1 kilometer in height, and the equilibrium level is 12.5 kilometers here. However, as we will see, the actual height of the cloud, simulated clouds, will be around 6 kilometers. So this suggests the impact of entrainment to the phenomenon. And we have some initial perturbation, and the next explains the CCN activation models. So we provide two types of CCN activation models. For models using 2D model, we suggest the participants to use these parameters, but limited by the maximum number of CCN aerosol particles by 1,150 cubic centimeters. And for models that consider aerosol particles explicitly, we suggest the participants to use the bimodal log normal distribution of ammonium bisulfate described in Tanzanten et al. 2011, but with the number concentration multiplied by 11. And as a result, the total number of aerosol particles will become the same, 1,150. So these two kind of aerosol particle setting is not the same. This figure suggests a difference. It's comparable, but not completely the same. And the domain size is 10 kilometers times 8 kilometers. And the grid width is uniform and 50 meters. And we have the boundary, surface boundary flux from the lower boundary, and it's fixed as constant. But for the first one hour, we have a uniform flux, horizontally uniform flux from the surface, and this is actually for spin up the turbulence in the boundary layer. And the rest of the time, we switch it to a Gaussian shaped flux centered in the middle of the domain to initiate cumulus congestus convection. What's next? For the control case, we do not consider collision coalescence, just consider the activation of CCN aerosol particles and their condensational growth and evaporation, and also deactivation. Okay, that's it, I think. Here is some recommended sensitivity tests. So we suggest the participants to decrease the CCN number concentration by a factor of 2/11, and if possible, also 4/11 to CG impact. And in that case, we suggest them to turn on the collision coalescence and see the precipitation. From here, I have some slides explaining the recommended outputs, but I'd like to skip this part for today. And also some definition of variables follow. That's it for the case description. Any questions? I don't know how to go back. Yes. Any questions? Is that okay? Then let's move on to the next talk. Again, this is by me, and it's a report of the scale STM results. Let me share the screen once again. Wait a moment. How I can do it. So okay, let's discuss the report of scale STM. This is a collaboration work with Toshiki Matsushima from RCCS and Seiya Nishizawa from RCCS. So, in short, I use scale STM particle-based model to test the case, and I also tried the case with smaller number of aerosol concentration with and without collision coalescence. I also swept the super droplet number concentration from 4 to 1,000 to check the numerical convergence. But I don't go into detail today, just very quickly. So this is some detail about the model. So scale is the name of the basic library for weather and climate models being developed by RCCS, Riken, Japan. And it's based on fully compressible non-hydrostatic equations. And I used this scale as a dynamical core and implemented the super droplet method STM to scale and I call this scale STM. So this table shows a numerical setup for the control simulation. And what's important here is that yes, it's very compressible equations. And okay, let me again turn on the laser pointer. Okay, so we consider condensation and evaporation with explicit CCN activation and deactivation. And what else? For the control case, I use 128 super droplets per grid cell. And for the subgrid scale turbulence model, I use Smagorinsky and Lilly model for the flow or the dynamics. And no subgrid scale model for microphysics to super droplets. In all the cases, I tested 5 ensembles. Okay, maybe that's it. And for the sensitivity test, is I decrease the ozone number concentration and collision coalescence on off. And yes, this is, I think I already explained. But remember that this is how I label each experiment. The aerosol number concentration, the collision coalescence switch on off, and the number concentration of super droplets, and the index of ensemble membrane. Now let me show you the results. So this is a horizontal, vertical cross section in the middle of the domain. And this shows cloud top height for various experiments. So for the left column, throughout these slides, I use this left column for non-CC case, collision coalescence case, and right column for experiment with collision coalescence. And for the top row, I use this for 11 VG case, the original aerosol number concentration experiment, and the middle for 04 VG case, and the low row for 02 VG case. So we can see the cloud top height is around 5 ± 1 kilometer, and the convergence, numerical convergence is good. But if you look at the number concentration, cloud droplet, and rain droplet number concentration, you can see the convergence with respect to super droplet number is relatively slow compared to the previous slide. And from this, I can say that the number of super droplets has to be more than 128, about 100. This is a time series of the total liquid water mass, and the convergence, numerical convergence seems to be better now. I picked up several ensemble members' experiments to show what's going on here, and I found that there's some oscillation in the, how to say, total liquid water mass. And this, I already confirmed this is not a boundary effect. Finally, this is a time series of the accumulated precipitation amount. So as expected, we do not observe any precipitation for the non-collision coalescence case, but for the collision coalescence case, we observe precipitation mainly in the third hour. even for the 11 BG case. And we can see the scatter of rain is big. And also from here we can see 4 super droplets per cell is too small, too few to simulate precipitation. Seems 32, 64 is much better, but 4 is very different from others. And this is a vertical cross section snapshot of the vertical cross section, but let me skip this part. So this is number concentration, has 2 different time steps. This corresponds to the peak of the oscillation of the liquid water mass, the first peak and second peak. And this is effective radius and the droplet size distribution with standard deviation of the droplet size distribution and K parameter and liquid water content, AF adiabatic fraction. Now this is a vertical profile of the number concentration. So this is a horizontal average of the 2 snapshots. So here we can see that it's almost constant with height. And the droplet number concentration decreases as the aerosol number decreases. And this is for 100 super droplets case. And I also prepared a 1,000 super droplet case. Here we can see the mean value is almost the same. But I noticed that the, width is narrow in this plot. For 100 case, it's somewhat scattered around the mean, but it seems to be more narrower if we use 1,000 super droplets. I noticed this for the first time a few hours ago. So I have to think more about what's going on here. It's good to know that the average is consistent, but it seems to be the super droplet number concentration seems to have some impact to the distribution, width of distribution. And again, this is for 100 super droplets case, and this is a vertical profile of the effective radius. You can see that it increases with height as observed in nature, and it gets larger as aerosol number decreases. And this is for 1,000 super droplet case, and I think it's very similar. Next, this is a vertical profile of the standard deviation, sigma, the width of the droplet size distribution. And again, it increases with height as observed in nature, and it broadens more as aerosol number decreases. And again, 100 super droplet case and 1,000 super droplet case looks very comparable. And this is a vertical profile of K, but let me skip this slide. And this is the vertical profile of the liquid water content. And here we can see, okay, the black line here, and the black dashed line corresponds to the adiabatic liquid water content. So all the liquid water content has to be lower, smaller than adiabatic liquid water content. But we can see some grid cell exceeds this theoretical limit. And this is due to the randomness of super droplet article-based model. So this is 100 super droplet case, and this is 1,000 super droplet case, and we obviously see the tail of this distribution kind of reduced, eliminated. Once again, 100 case and 1,000 super droplet.
Shinichiro, you're going over time now.
Really? Okay, let me finish. What else I have here? Okay, finally, this is the local droplet size distribution categorized by G and AF, but I will show you again later during the discussion session. So let me skip this. So this is inspired by Kamal's analysis, and yes, this is something interesting. And this shows a computational cost and summary, but I don't read this out. Okay, that's it from me. Any questions? Okay, no questions. Then let's move on to the next report. Again, it's from me. Wait a moment. I think I can finish this very quickly. So yes, this is the slides. This is a report of scale beam, and this simulation was conducted by Yosuke Sato from Hokkaido University, but unfortunately he is not able to join us today. So I'm speaking on his behalf. So for now, let me just explain the detail of the model, and let me skip explaining the result. I will show you some result later during the discussion. So he's also using scale was a version. So the version is slightly newer than what I used. What I used was 5.2.6 or something, but he's using perhaps the latest one, or very close to the latest one, 5.4.1. But there should be no big difference between the two versions. And he used spectral beam model, and it was one model developed by Suzuki et al. to 2010, and this is based on Hebrew University Cloud Model, UCM. I think this is the one Kyung-ok is using with WRF.
Shinichiro, are you sharing your screen? I don't see your screen.
Really?
I think the screen is not shared.
Sorry. Yeah.
Okay.
Okay. Can you see now?
Yes.
Okay. So the version is 5.1, and the detail of the spectral beam model. One moment, developed by Suzuki, and it's based on HUCM. And this is again some detail of the numerical setup. What should be mentioned right now is that because this is a beam model, he used the Toomey activation, and also this is the beam layout from 3 microns to 3 millimeters with logarithmically uniform widths. I think 3 micron for the first bin would be too big, but let's discuss this later. I think that's it for now. 100 bin case, and it's not written here, but he also tested 60 bin case and 33 bin case. That's it. Any question or comment?
So, Shinichiro, my comment would be that 100 bins is quite high number, and my experience is that with a single moment scheme, this is a sensible choice. And to remind people that are not familiar, the classical kind scheme uses 33 bins, which in my mind is very low, and a lot of publications are done with this scheme using 33 bins setup. So this is really low. My experience with scheme that I coded up was that I need to have actually more than 100 bins to be comfortable with, based on a partial model. But so 100 bins is something that I would consider a sensible choice. That's basically a comment. It's not a question.
Okay, thank you for your comment. But actually, I will show you that it seems 33 bin is working okay. Okay, let's discuss this later. I'm surprised to see that. Let us discuss this later. Any other comments? If not,
Adrian, this is Lulin. Would you mind raise your hand so that I can spotlight you? Okay, now you are spotlighted, so you can speak now.
Got it. Hi there, Shima. This is Adrian Hill. Just made it in today. I couldn't make it here yesterday. So I just wanted to follow up on what Wojtek said there. I agree with him actually about the 100 bins for single moment, but it's I'm sure Wojtek, I don't need to say this, but if we're running double moment, we don't need to run with anywhere near that number of bins. Sort of in the 30s seems okay, and it seems to do as well as number of bins in the hundreds for single moment. So again, it's a bit like Wojtek. It was just a comment rather than a question. Sorry.
Yes, and I agree with that. And then, of course, the cost is comparable, because with double moment scheme and let's say 50 bins, the cost is comparable to single moment 100 bins, because, of course, the most expensive part of the bin scheme is moving around all those bins. So, when you get double moment scheme, you have to add twice as many variables. So it's kind of comforting to know that you need to have fewer number. And I think I don't remember whether Kamal will be talking about that, but we actually have two schemes comparing double moment, single moment directly. And that's something that Kamal is doing, I think. I'm not sure. Of course, I'm in Warsaw and he is in NCAR, so we haven't seen each other and didn't talk to each other for quite a while, actually. So anyway, but let's not waste any more time. I think Shinichiro, I think Kamal is coming next, so we will see what he will be talking about.
Okay, let's move on to the next talk. And yes, next speaker is Kamal. Are you there? Okay, you are already on the podium. Okay, so yes,
Kamal, you're unmuted.
I'll share my screen.
Yes, please start.
Can you see my full screen?
Yep, you can see.
Okay. Yeah. So hello everyone. Today I'll just briefly introduce the model setup and the simulation I'm doing. So this is the isolated stimulus congestus cloud simulation using CM1 LCM and CM1 framework. And this work was done in collaboration with Wojtek Grabowski, Hugh Morrison, and George Brand at NCAR. So the modeling framework for this simulation is CM1, which is NCAR's model developed by George Brand. And we are using CM1 in LES configuration with the prognostic subgrid scale turbulent kinetic energy scheme. So we use compressible solver with some time splitting, and yes, and we integrate the zoning equation with RK and time integration with the Fowler direction scheme for velocity and scheme for scalars. And for microphysics, we have implemented this super droplet method from Shinoshiro, and that has advection of support particles using predictor corrector method, and has explicit aerosol activation with curvature and solid terms. And for condensation growth, also we include those effects, and we solve that condensation equation using backward Euler method with Newton induction method for finding root. And it has stochastic collision coalescence scheme developed by Shima, and we also implemented subgrid scale scheme for particle transport that's based on Lagrangian stochastic approach developed by Well et al. And we also have a subgrid scale scheme for supersaturation fluctuation and condensation that's based on Sarina, Grabowski, and previous work. And for beam microphysics, we have a double moment beam microphysics scheme that's that's based on the Tel Aviv University's beam microphysics scheme, and it has 35 mass doubling beams with total 70 beams, and we have added additional 20 beams for aerosol advection. So the simulation configuration for our case is based on International Cloud Modeling Workshop this 2021, and funding from small team of microphysics study field campaign. And the domain size is 10 km by 10 km and 8 km in vertical direction. And for the control simulation, we have 50 meter grid resolution in all directions, but we also did some tests with a higher and a lower grid resolution. The initial super droplet concentration for this case is around 120, average of 120 super droplet per grid box. And we integrate the governing equation with 0.5 second time step for dynamics, and for SGM microphysics, we use smaller time step of 0.1 second. The aerosol concentration is similar to what Shima described. It's 11 times Van Zetten all. And we also did some simulation with lower concentration, and actually it's lower than what's described in the case setup. Like we use basically one time Van Zetten et al. And for that case, we have both the runs with and without collision coalescence. But for the control simulation, we just use 11 times Van Zetten et al. Aerosol concentration, and we just have a case with only condensation, not collision coalescence. And then surface structures are similar to the case description. And we use 5 different flow realization for only condensation case. So here's one example of left plot shows the cloud water mixing ratio at different times, and the right one shows the cloud base and top. So the cloud base is close to 1 kilometer, and then it's very similar for all realization. Cloud top varies considerably, and the maximum goes around 4,500 meters after around 2 hours. And this is similar for both beam and SGM microphysics. So here's some example of super droplet trajectories. So you can see different trajectories reaching different target grid cells, and some trajectories are straight going to those target locations, but in some cases the toroidal circulation in the cumulus cloud leads to entrainment and variation in the droplet trajectory. This has impact in the droplet growth and activation. So here's some sample droplet size distributions at different locations. So this is based on the run without a good scale model for microphysics. And you can see near the cloud base, there's some variability in the mode radius, and I think this image Shima also shows similar effect, and that could be due to the variability in the cloud base, as well as some activation at different regions near the cloud base. And then as you go higher and higher, the mode radius increases, but also you can see the distribution with the lower adiabatic fraction has the left side, like a larger or bigger left side trail, and that basically changes with the adiabatic fraction range. So for the most diluted range, you can see a more pronounced left tail in the distribution. With subgrid model, this left tail become more pronounced, and in some cases you will see bimodal shape in the droplet size distribution. But without subgrid model, that bimodal shape is not very clear. So this is again vertical profile of cloud properties like mean radius and vector width. From left one is from super droplet method, and right one is from cloud beam microphysics. And you can see the mean radius is very close and very similar for both two cases, and has an expected trend. And but the spectral width is very different. Like the mean value at the top of the cloud is around 2 micrometer for the SDM, and for beam microphysics it's nearly 4, so almost double spectral width for beam microphysics scheme. So that's most likely due to the numerical diffusion from vertical aggression of beams. So we have additional data set, as I explained, like with subgrid model as well as with lower aerosol concentration, but it was not submitted as a part of this case because of the difference in the subgrid scheme and also aerosol concentration that yeah. So here's one example from those simulations. So this is the top plot shows the cumulative entrainment activation height. Basically, this top right plot shows the amount of activation at or below that level, and you can see the significant activation at cloud base as expected, but then with increase in height, there's a linear increase in the overall activation and as well as entrainment of aerosols. And the second, when you integrate this, and that will give the secondary activation total amount of secondary activation that's around 25% of the total activation in the cloud. So this is a significant amount, and that this secondary activation affect the cloud properties significantly. So, for example, in the bottom we showed spectral width versus adiabatic fraction, and as you can see that for the left plot, which is for the control case where we have secondary activation, the spectral width increases with decrease in adiabatic fraction as expected because of the entrainment. But in the most diluted region, it decreases So to understand this, we did a simulation where we turned off secondary activation. We found that in the less diluted region, the spectral width is lower compared to the case with secondary activation. But this decreasing trend is nearly absent in the very diluted part, and that confirms that this decreasing trend is because of the secondary activation. So this
Kamal, you need to finish soon. We're running out of time. Okay, good.
Yeah. So just a few more slides. So we also did some simulation with droplet collision coalescence, but as I said, we used lower concentration than described in the case description. So this is one vertical snapshot at the center of the domain, showing cloud rainwater mixing ratio at that vertical size. So the top one is from SGM, and the second one is like basically applying a Gaussian smoothing to super droplet runs, and the third row is from Taubin microphysics at different times. So as you can see that rain started forming early in the Tau run, and also more it's more significant, and then it grows more and more with time. But also the SGM run also has significant rain formation, and slowly started catching up. But but at the end of the simulation, also there's also difference in the rainwater content in those two runs. So this difference is because of the change in the difference in the spectral width in those two schemes, but also it also due to the difference in the rate of autoconversion accretion in Tau and SGM. So I'll just stop here. Thank you.
Thank you. Any questions?
Okay.
I have a short question. What is the beam layout for your tau beam simulation?
Yeah, so basically we have like minimum radius, minimum size around 1.56 micrometer, and then and then 35 mass doubling beams. So
So 1.5 micrometers in radius, right?
Yes.
Okay. Thank you. Any other questions, comments? If not, then let's, by the way, if you have any questions or comments, please raise your hand. You know how to raise your hand. Or if you really want to talk without raising your hand, if you come to the front and there's a podium and the chairs here where I am taking my seat. If you come here, you will be spotlighted automatically. So, okay, let's move on to the next speaker. So thank you, Kamal. And let's move on to the next talk, and it's by Kyoto Oji-kan. It's on UW-LCM result. Please unmute.
Yes, can you hear me?
Yes.
Okay, I will try to share my screen.
I think you had yes, today you can see your screen.
Yes, today I'm using Windows. Yesterday I was on Linux.
Okay.
Okay, so I will talk about the simulations done with the University of Warsaw Lagrangian cloud model. And most of this work was done by Piotr Żmiecki, who is a PhD student in our group. So UW-LCM uses the anelastic approximation. It uses the MP data algorithm for advection and super droplet microphysics. We can also use bulk microphysics, but for these simulations we used super droplets. And for subgrid scale diffusion of Eulerian variables, we can either use the Smagorinsky scheme or no scheme at all, what is called implicit LES. And for subgrid scale diffusion of super droplets, we either use the a simple scheme from the Grabowski and Abade paper or no scheme at all. So the setup was follows the case description. It's a 10 by 10 by 10 kilometers domain. We use an absorber above 9 kilometers. We model 3 hours, and for each case we do five simulation runs. As for the time steps, the model time step is half a second, and condensation coalescence are modeled with 0.1 second time step. Okay, here's a list of all simulations that we did. You can see the resolution, the type of the subgrid scale model used, the aerosol concentration, number of super droplets, and if coalescence was modeled. So in this main set of simulations, we didn't use any subgrid scale models, and we did model collision coalescence. And we did simulations for 3 different aerosol concentrations, this clean one, intermediate one, and polluted one. And for each aerosol concentrations, we did runs for 2 different resolutions and for 2 different numbers of super droplets. So that way we can draw some conclusions about how the results depend on concentration, on resolution, and on number of super droplets. We also did some tests in which we use different subgrid scale models that I will not talk about, but the general conclusion was that these subgrid scale models do not change results much. Okay, so first I will show how the liquid water mass changes with the model resolution. So here we have results of the polluted case. These are time series of liquid water mass, cloud water mass, and rain water mass. In this polluted case, there is no rain, so it's only cloud water. And on the left, okay, these dots are the averages from this ensemble of 5 simulations, and this shaded region is one standard deviation range. So on the left is a result for a high resolution, 550 meters, and on the right with a lower resolution. So please note the differences in the vertical axis, and then you will see that we get more liquid water if the resolution is higher. And next we have the same plots, but for this intermediate aerosol concentration. Again, there's more liquid water for higher resolution, and we see some rain developing, but very little. And then in the clean case, again, there's more liquid water if the resolution is high, and there is significant amount of rain developing. Okay, next I'll talk about how liquid water mass depends on the number of super droplets. So first from the polluted case, again, it's the time series of the liquid water mass, and for 100 super droplets per cell here on the left, and for 500 on the right. Well, we don't see any clear effect clear differences between these two. So we conclude that number of super droplets does not affect liquid water mass. And then for the intermediate simulation, aerosol concentration, we see the same. And for the clean case as well, we have the same, basically the same amount of liquid water for these different super droplet concentrations. But then if we look at surface precipitation and how it depends on number of super droplets, we start to see some differences. So this is the accumulated surface precipitation from the clean case, and this is for, again, this is the lower super droplet concentration and higher super droplet concentration. And you see that for 500 super droplets per cell, we get significantly less surface precipitation than for 100 super droplets. And we did not find any obvious reason for that. For example, if we look at the number of droplets, which is plotted here, these are vertical profiles of the number of droplets at the moment of the first maximum of the liquid water mass. And we see that they are quite similar for both super droplet concentrations. If we look at the radius, these are profiles of the effective radius. Again, they are quite similar for 100 super droplets and for 500 super droplets. So some conclusions that we can propose are that for high resolution, we get more liquid water, which is, I think that it's not very controversial. People tend to see this, but also we get we find that when using more super droplets, we get we get less surface precipitation. There's an error here, and we are not sure why it is so. And I wonder if other groups also see this effect. Thank you.
Thank you. Any comments, questions?
Piotr, can I ask a question?
Yes, go ahead.
So you only covered 2 number of super droplets. I think it would be interesting to see kind of some range, go even lower than 100 and go somewhere in between. Yeah, and it's actually, of course, the other possibility is try to use different way of calculating collisions, go away from Shinichiro's algorithm into some other ways of calculating it. Of course, the Shinichiro algorithm is very clever because you keep the number of super droplets the same, whereas in real world, when you get colliding particles, the number of particles changes. But I'm curious whether it would be worthwhile to look at some other ways of doing collision coalescence. For example, the way Mirek Andrejczuk does it, completely differently to kind of understand better what's going on. But it's interesting and puzzling results. So I hope you can get to the bottom of it, one way or another.
Yes, I think we will try with different super droplet numbers first, and then we will maybe we'll try different, maybe Mirek's algorithm. Yeah.
So this is just a comment, but as I showed you earlier, I changed the super droplet number concentration as well, but I didn't see a difference between 150 or 100 and 1,000. I see something similar when I use this number of super droplets. For super droplets, I observe the variation, but not for 100. So it's a little bit not consistent, but yes, let's discuss this.
But do you get more rain if you have, for example, 4 super droplets, or do you get less rain?
If I use this number of super, I had more rain. So yeah,
In this way, but not in the numbers. Okay.
Yes, exactly. Any other comments, questions? If not, we are a little bit behind the schedule, but let's have a 10 minutes break. Right? Wojtek, what do you think?
Yes, I think we need at least 5-minute break. Let's call it the bathroom break, and it's almost exactly 8 o'clock in Colorado. Maybe we can have a 5-minute break. Hopefully that would be sufficient. So let's meet in 5 minutes. Let's resume in 5 minutes.
Good. Then 5 minutes break. Now,
Yeah, I think we need to start. So please go ahead.
yes, let's restart the session. So next speaker is Kyung-ok Choi from University of Washington. She will report the result of WRF-UPNB. Are you here, Kyung-ok?
Kyung, you have to go up and stand in the speaker spot.
Yes, yes.
Can you hear me now?
Yes.
Oh.
Yes, you
Yes.
have to be there.
Yes, in there. Yes. Thank you.
And screen share for this, or
It's in the bottom of the screen, and there's a screen
okay.
share button.
Okay. Can you see my screen now?
Yes.
Yes.
Thank you. Hi, I'm Kyung-ok Choi, and this work is conducted with Ah-hyun Kim and Sung Soo-yeon from Yonsei University, Korea. Today, compared to other previous speakers, I couldn't conduct many sensitivity tests. So today I will focus on introducing the microphysics schemes we used and some settings that can differ from those of other participants. The WRF's idealized LES model is used, and microphysics scheme is Hebrew University spectral beam microphysics scheme. For cloud drops and CCN, there are 33 mass doubling beams, and cloud drop number concentration is calculated with this equation, and terminal velocity of cloud drop depending on the radius of cloud drop. Terminal velocity of cloud drop depending on the radius of cloud drop. The radius of dry aerosol is from about 0.001 to 2 micrometer, and cloud drop radius is from 2 to about 3,200 micrometer. If cloud drop radius is larger than 100 micrometer, the drop is considered a raindrop. CCN distribution is based on Toomey's formula, and height dependency of CCN number concentration of this microphysics scheme is ignored for this study. For drop activation process, critical radius of dry aerosol is calculated based on Keller equation, and latent heat does not release in this process. And the radius of newly formed cloud droplet depends on the size of dry aerosol particle. After diffusional growth process, cloud drop distribution is remapped with covert and Orland method, and this method induces a significant droplet spectral broadening. In the Fuji SPM scheme, the modified version of covert and Orland method is employed, which reduces the spectral broadening. The top panel of light figure, and if droplet is completely evaporated during CCN regeneration process is necessary, and the original version of Fuji SPM scheme in warp model does not consider this process. So we implemented a CCN regeneration process based on Feingold et al. Collision efficiency increases with height, and turbulence effect on collision corner is turned on for this study. And breakup process for the large drops, the raindrops, are also considered in this microphysics scheme. This slide shows simulation setup, and vertical grid size is not constant in the warp model. Warp model's vertical coordinate system. So I just used the 200 layers for this simulation, and the range of vertical grid size is from 32 to 63 meters below 6 kilometers, which is approximate maximum value of cloud top height during simulations. Also, rally damping is not considered due to the conflict with other settings. And 3 simulations are conducted, and control case is follow the cumulus congestus case specification for this workshop, and simulations to assess the effect of collision coalescence and decrease of CCN concentration on the clouds are also conducted. And this slide shows the cross-section of liquid water content and drum number concentration at the center of surface forcing. And collision coalescence process causes surface precipitation. And how about the clean case, which decreases the CCN number concentration? There are some raindrops, but no surface precipitation for this case. Here are time series for 3 simulations, and cloud top height are not much different among 3 simulations, and also the main average water pass is the maximum values are not very different. And yep, this is all I have today. And any questions?
Thank you. Hello. Any questions? So let me confirm. So your low air zone concentration case, you didn't switch on the collision coalescence. So it's without collision coalescence.
No collision coalescence for that case.
Okay, I understand. That's why we do not observe any precipitation for that.
Yeah.
Any other questions, comments? If not, let's move on to the next speaker. Thank you, Jong-ok. So next speaker is Luling. He will report the result of WRF-UPNB.
Okay, thank you, Shinjo. And before I start, everybody, if the audience is here is beyond 100, then the screen sharing and spotlight speaking will have technical difficulty to reach everybody. So in that case, you're welcome to go to the right-hand side of the room. There are multiple entries marked that when you get to that right-hand side room, you will see a screen that when you press X, you can see the live stream of the YouTube live stream. So it's very useful and simple, and you can still ask questions in the chat or raise your hand. So that's kind of a doubled our capacities in that way. So far we haven't reached that level, so everybody is welcome to stay in this room. But when that happens, you have more choices to watch our presentations. So that's a short notice. And let me share my screen. And I hope you can see my screen. Can you see my screen?
Yes.
The full slide mode?
Yes.
Okay, thanks, Shinichiro. And our group tried to be part of the intercomparison using WRF as the dynamic core, and also the UPNB is the University of Page and NCAR beam scheme as a microphysics. The work is mostly done by Jinghua Chen from Nanjing University of Information Science and Technology. Ishvan, Noemi, and myself are involved. But due to some personal kind of the issue that Jinghua didn't make much progress since the last mini workshop, I still want to just give quick updates. But we do have plan to run this case with more according to the workshop requirement in the future, and also extra work in the piggybacking. So I'll briefly cover those. And also save time for our discussions later on. Kyung-Yeok made a very good introduction on kind of the WRF, how we use WRF to simulate this case. The setup is the same as Shinichiro put forth, and the fluxes and also the momentum fluxes are modified in different files in the WRF model. And mostly the surface layer physics, so we can include both effects in these modification. And also the soundings were provided by the case description and also Sonia's study in the past. And we don't use any shear in this case, but I think maybe in the future, that'll be good to look at some of the shear impact, but it could be outside of the scope of the intercomparison. We tried to run this with the required size and resolution, but due to the computational cost, we use 100 meter for our beam simulation, but 50 meter for a bulk test. So for any other participant or any researchers that are interested in this case, you can actually run your bulk scheme for checking the dynamics and the regular cloud and precipitation processes. But for this specific comparison, we want to see the distribution between beam and beam and STM. So that's why we need to run this at least for the beam microphysics. So here we use the UPNB. It's a 36 mass doubling beam scheme, and we turn off the ice processes and use water only. And then there are two TUMI kind of type of CCN activation curves that have been used. But I need to recheck with Jinghua to make sure those numbers are aligned with what's being asked by the case. So far, we were able to turn on the rayleigh damping in top, different than Kyung-Yeok's result. Other than that, we're very similar. And I think Shinichiro asked the computational cost from last mini workshop. So we put forward this this number. and it's about using 28 cores is about 1:1 to run the bean, to run the bulk. But to run the bean, even with a coarse resolution, we need about 14 hours to run 3-hour simulation using 84 cores. Here are some of the preliminary comparison. This is from the bulk microphysics, and we run this this bulk with so many different CCN concentration, and just to check if it's if the result is sensitive to this specific variable. And we noticed that there's some trends, but we didn't put up the ensemble realization into this. So I personally think there are some distinguishable differences, especially the red curve, and compared to others, but they're kind of still within the kind of the uncertain ranges that being posted by different realization of the flow. For the bean, we only have like 2 brief tests, but we also noticed the cloud top, at least from the higher CCN case, reach to the high level compared to the lower CCN case. By the way, we didn't turn off the collision coalescence, so we do see rain from both bulk and bean simulations. For the AF adiabatic fraction plots, we also make similar contour, 2D contour, similar to what Shinichiro used. And here it seems like the early development stage, there are not that many differences between different CCN concentration. Even in the vigorous growth period, still we only have the core region have higher. We don't have really like a very many points with very high AF. Mostly they are still in a very low AF region, indicating a very strong mixing and entrainment in this case. But for interestingly, for low CCN, we kind of and super high CCN, we see some high AF value. But I believe this is still part of the realization issue that we cannot robustly conclude they are the feature of these 2 CCN scenario. And also you can see in the dissipation stage, the clouds are so different in these runs. And in the bean simulation, we saw some similar feature, but for development stage, we do see more higher value AF. And later on, it seems like the control CCN, supposed to be lower CCN number concentration, shows more high AF value compared to the high CCN case. But the top is higher in the polluted scenario. In the dissipation stage, they become also similar. And I didn't make the animation for the central cross-section, but our cloud seems to be a little bit broader and gets wider into the domain compared to others. But I think we will probably reprocess the data and make sure that we have a similar aspect ratio, so we can see the structure compared to others. And for the bean results, it seems to be even wider. And here are some time series of the cloud water and the rainwater mass. I think it's the mean mass, the mean mixing ratio, I would say. And then as you can see, for the bulk, they're aligned with each other, but there's some trend of early rain formation for the low CCM, but not so much like a monotonic kind of no monotonic trend in the timing of the precipitation development along with the CCN number. And the bin scheme, we also notice the cloud water cloud water are very similar between the different CCN case, but the rainwater, interestingly, in the higher CCN scenario, it gets more rain. So it's slightly different than we usually see, but as I pointed it out, realization issues and uncertainties can explain this. And I have to put up these very high-level bullets here, and due to the personal kind of the constraint that Jinghua has, we didn't make much progress. But now we will move on to this case with Ishvan and Noemi's help. So we will probably make better results and outcomes in the coming month or the next several months. And we do plan to run piggybacking using this specific setup. So that's all I have, and I'll give it to Shinichiro.
Thank you, Luli. Any comments, questions? So I didn't notice that you
Go ahead.
So yeah, maybe I kind of compare the result of bulk model with others. So please after each case report, each model report, we have some discussion, and I prepared some slides to compare the result with each other. And there, if I'm plotting something different, not the result of being, but the result of bulk, please just let me know.
Okay. Yeah. Sure. I think I think Jinghua recently just made the bin rounds, so that's why. Yeah, that's why you didn't get it. So sorry about that. Yeah.
I see.
Okay.
Makes sense. I was a little bit puzzled by the result and the especially the computational cost too fast. So I was wondering what's happening.
Okay, sorry about that, but yeah, I'll make sure your comparison. I'll explain what's the actual data there. Okay. Thank you.
So if no more question, comment, then let's move on to the next. So thank you, Luli. So next speaker is Wojtek Grabowski. He will present his result of OIRAC. Yes, Wojtek, already on speak.
I started to share my screen. Do you see it?
Not yet. I don't see.
I don't know what to do. I see it on my screen, so I don't know how can I. Oh, maybe I should hit the button at the bottom of my screen.
Yeah.
There we go.
Then after that, you choose which screen to share.
Okay. You can tell that I'm not very efficient in those things. Okay.
Yes, but I don't see your screen. Okay, let me try. So here now I'm sharing my screen and
my talk. Am I right?
Sorry.
And you will show my talk. Am I right?
I think yes, I can do it, but please just try pushing this button here. Here.
Yes, I did that. Then I see share.
Hi, you have to select the window that you're sharing and then click share.
Okay, there we go. Okay. Oh, now I see it. Okay.
Yeah. Yes. Okay.
You
yes, we can see it now.
Yes,
we can see it now. Yes.
All right, very good. Sorry about that. That tells you how efficient I am in those computer-related things. So anyway, this is kind of old news, which last year, if we would have this workshop last year, there would be news. This is old news. As you can see, the paper that I will be showing some results from has already been published last fall. And as Shinichiro already pointed out, the case comes basically from Sonia's paper. We kind of tried, Sonia gave us some hints how it was done, this and that. We tried few things, and we came up with the setup with Shinichiro. So at the right-hand side, you can see the kind of a cloud from the original paper. So the only thing that is kind of specific for this paper and for my simulations is using the piggybacking. For some of you that are not familiar with this term, I'm supposed to explain it right now. So basically what piggybacking is about is that you run one simulation and you use two microphysics schemes. So in this case, we'll be bin scheme versus Lagrangian scheme with super droplets, and I will only talk about condensation. I haven't done a precipitating cumulus case yet. So the idea is that you basically run two simulations, but the first simulation, the dynamics is coupled to the thermodynamics. So this will be, let's say, bin scheme here. And then, but you also run super droplets in a kind of a kinematic framework. So that's where piggybacking comes, the name of piggybacking comes about, because this super droplets in this upper panel kind of don't affect the flow. So they're piggybacking the flow. But to be kind of honest for the simulation, then you run another simulation that actually dynamics is coupled to super droplets, and bin is piggybacking the flow. So by doing these two experiments, you of course have different flow realizations in each of them, but in one of the simulation and the other simulation, those two microphysics schemes operate with the same flow. So that's the advantage, because the impact of the realization is taken out. Yes, there are different flows in those two simulations, but at least in one, the scheme interact with one flow, and in the other, the two schemes interact with another flow. So as I will show you, for example, if you take a snapshot of the cloud field in one of those simulations, they will basically look very similar. So I will skip this slide. You know what super droplets and what the bin scheme is, so I will skip that slide. Now, here my summary of my results, and one thing that you can immediately notice is that my clouds go deeper, much deeper than other clouds, and we still haven't done work to understand why it is so. I don't think it matters for the comparison, but that's the fact. So this is the cloud top evolution, cloud-based evolution, and center of mass. So you can see that the bin versus super droplets is really not that important in the simulations. The dynamics, the mean updraft, so it's kind of an updraft averaged over cloudy points and with some threshold value, are kind of similar up to the kind of last few, maybe 15 minutes. This is an important information here. This is the total cloud water mass. And again, the solid lines are from driver, dashed lines are for piggybacker. So red color is bin, the blue color are super droplets, and you can see that there are some significant differences in terms of mass of cloud water. Basically, the bin, the red color, is lower than the blue, so it means that there is more evaporation. So I had some similarities and differences here. So microphysics has a small impact on the mean updraft and cloud top rise, but bin microphysics seems to provide more dilution. Now, where this dilution is coming from, and this is just another illustration. So as you can see, the cloud look kind of similar, at least the outline of the cloud in these two, because this is just one simulation. I don't remember which one drives, which one piggybacks. That doesn't really matter. The point is that I selected 2 points, one kind of near the bottom of a cloud, and another somewhere higher up when there is quite a bit of dilution. And On the left-hand side, you can see results from the bin scheme. On the right-hand side, you get results from super droplets. And one thing that you can immediately see is that at the low levels, the size of droplets and liquid water content are kind of similar. Sorry, oh Jesus, I hate this. But then if you look higher up, this is basically the point that there is less water and the droplet size is slightly lower for the bin scheme. But more importantly, there is significantly less water. So there is also more fluctuations in the Lagrangian microphysics. This is because this simulation doesn't have tremendous, very high number of super droplets. But even with let's say 100 super droplets, statistical fluctuations will be like 10% if you get the same multiplicity. Anyway, so sorry about that. So this is the comparison between, those are relatively complex plots, but I hope you will get the main point because this is piggybacking. At every point, you get two values, one from the driver and one from the piggybacker. So point by point, you can compare, for example, potential temperature, point by point. Those are at different heights. Color represents different heights. You can compare water vapor between those points, point by point, and you can see those bulk temperature and water vapor compare quite nicely. But now, if you look at the cloud water, there is significant scatter, and it around this 1-to-1 line. Of course, this comes from the fact that the bin microphysics is diffusive. That's one thing, but also the super droplets have this inherent limitation of statistical fluctuations just because limited small, typically relatively small number of super droplets per grid box. Now, the buoyancy, as you can see, is also scattered a little bit, but well, at least with those scales, not as much as cloud water. So those are bulk properties. Now, if you look at the microphysical properties, so this is mean radius from super droplets versus bin mean radius, and you can see at low levels, those blue colors, the comparison is pretty good. But if you go higher up, about 4 kilometers, you see that most of the points, not all, but most of the points are below this 1-to-1 line. Below means that super droplets radius is larger than the bin radius, okay? So that's why those points are below. Now, if you think about spectral widths, and that was already talked a little bit, that bin microphysics tend to have excessive spectral widths, you can clearly see it in this plot. Even at low levels, when below 2.5 kilometer green points, you immediately said that the bin, those points are above, so that means that your spectral width is larger for the bin microphysics. And if you go higher up, then of course there are some points when below that are below the 1-to-1 line, but most of the points are above. So this is this problem with the bin microphysics, at least the very particular that I use, my own single moment, not that many bins, but that's the issue. Remember, there is only condensation here. So even, I think I get like 40 bins, so even with 40 bins, only condensation, that's a pretty high number of bins for condensation alone. So key conclusions, piggybacking allows point-by-point comparison of cloud properties independently from the specific cloud flow evolution. So that's kind of the last plot was kind of highlighting that. And the simulations expose key drawbacks of the two modeling approaches, numerical diffusion in the bin scheme, and the limited number of super droplets that the Lagrangian approach can afford. So basically, that's what I said at the beginning. The paper has been published. There is more analysis of those simulations. And I think Shinichiro will be talking about comparing model results, and you will see that something that I still have to work on and understand why my clouds are deeper than other clouds. My initial kind of look into that some time ago didn't really kind of point me in the right direction. So this still remains to be seen. So this is it. Thank you. So I stopped sharing, although maybe I already did.
It's unshared. Thank you, Wojtek, for your talk. Any comments, questions? Yes.
All right, Adrian, you are able to speak.
Hi there, Wojtek. So I just was wondering, well, two things. One, I probably missed this at the beginning. So those runs were just condensation. There was no sedimentation.
Well, I don't remember exactly. I think at a 50 meter, the sedimentation really doesn't matter if you have just condensation. I mean, you can have it, but it really should have no effect with those droplets falling, you know, I don't know, 10 centimeters a second max. So I don't think it matters.
Yeah, okay, but it might do at the edges. That's the thing. It might have some impact on your turbulence at the edges.
Yeah,
so if you've got a difference in the sedimentation fall velocities between the two models, that could send your simulations off in slightly different directions with size.
Possibly, but remember, this is piggybacking, so the flow is the same. The flow is the same, and I don't think I had sedimentation because, as I argue, you know, the 50-meter grade and no collision coalescence sedimentation should really matter very little. So, okay, so that's one.
Yeah, no, that's okay. So just one other quick thing then, with your clouds going too high. So, I mean, we've seen this before. We saw this in, I mean, this is with mixed phase clouds, but in TWP ice and stuff. And it was to do with the lack of dilution that you get with the resolution that you pick. So you could, well, maybe not simply, but just try a higher resolution and see if you still get too high liquid water content, too high cloud tops.
Yeah, and I don't remember exactly that, but I think I did, but not with the bin scheme. I did some tests with bulk model, higher resolution, and yeah, I mean, I shouldn't say because I don't remember, but that's something that needs to be. I mean, of course, you know, it's not like the cloud cannot go up there because, as Shinichiro showed at the beginning, the equilibrium level is, you know, somewhere above 10 kilometers. It's just that dilution limits it. So yeah, there is definitely a suggestion that maybe for one reason or another, I'm not diluting as much as other models, although I will be quite reluctant to kind of, you know, based on my results, kind of use that. I mean, I definitely need to look into that. And that's something that has to be done. I simply didn't have time to do it.
Yeah, no, it's good talk there. Thanks, Wojtek.
Thanks. So I think, Shinichiro, I think this is a discussion period, and I think you have some slides to show us. Am I right? So
that's right. Then shall we move on to the discussion session?
Yes, I think so. We are about 15 minutes behind. So if the discussion kind of lasts too long, then we may want to cut it a little bit after the allocated time. But otherwise, you know, the floor is yours, and whatever you prepared, please show us. Yes.
Yes, I will share my screen and show what I prepared. I compiled all the results for this discussion. So wait a moment, please. So do you see my screen right now?
Yes.
Okay.
Yes.
Then let's start the discussion session. So let's start from the end of this slide. I summarized the result and what I think we need to discuss. Wait a minute, how to go to the end. Yes. So regarding the control case, I confirmed that the bin scheme result and particle-based model results compare well, except Euler and WRF-UPNB. And maybe I checked not the result of WRF-UPNB, but WRF with bulk model. And I say that Euler doesn't compare well by the fact that the cloud top height is too high for Euler. But the cloud microphysics characteristics compares very well with other models. And regarding the droplet size distribution, I observe that beam models are consistently wide.
Is it just me that I cannot hear you, or
Really?
other people can hear you? I cannot hear you. I see you muted, so maybe that's the reason.
No, we can hear Shinichiro. I don't know why you cannot.
What's going on?
Okay, so let me. Yeah,
I think we all can hear Shinichiro. Only you cannot. Can you hear me?
Yeah, I can hear you, and there are 83 participants, so I don't think that's the problem.
Hello. Can you
we can hear you, Shinichiro.
But it's funny because I see him muted, but kind of a different way. I see him.
Yeah, I think Wojtek, you have muted Shima, so you can unmute him yourself.
Okay, yes.
There we go.
Yeah.
Okay.
You can unmute him. Okay.
Yes.
Okay, sorry about that. Shinichiro, sorry about that. So go ahead.
Yeah. So can you hear me now? Wojtek?
Yes, I muted myself. Yes, I can hear you now.
Interesting. So I just explaining this part. So yes, the droplet size distribution. I observed that the beam models are consistently wider than particle-based models, and initially I thought that this must be due to the numerical diffusion of the beam schemes, or maybe due to the too big fast beam. I mean, the fast one, like 1 microns or 2 microns or 3 microns. This, of course, affects the cloud droplet size because we use it for the activated droplets, if I understand correctly. However, as I will show you later, scale beam, Euler, and scale STM all look converged already, numerical converged already with respect to the beam numbers and also the super droplet numbers. So it's a little puzzling for me. So let's have a discussion on this point. And the next remark is that liquid water content in a grid cell. And this is, we observe that this is larger than the adiabatic limit in particle-based models in the tails, less than 10, this is less than 10%. And this is due to the randomness of super droplets. This is something what already pointed out by in Wojtek's paper. He mentioned earlier. Regarding the sensitivity test, the test with low aerosol number concentration with collision coalescence process on, I couldn't draw any clear conclusion yet. First, the result of scale STM and UW-LCM do not agree very well. It's comparable, but do not agree well yet. And I still do not have enough amount of data for beam models. Next remark is that beam models seems to be converged numerically at 30 bits. This is a surprise for me, but I will show you what I observed. And regarding particle-based models, it seems hundreds super droplets per cell grid cell seems to be sufficient, though it is still noisy. And finally, the computational cost. It seems to be comparable between the two models. So let me show you some more detailed results regarding those related to those points. So first from here. So this is also the list of participants and the case I used for this analysis. So maybe I'd like to confirm right now that super high CCN case for WRF-UPNB is for bulk model.
Yes, super high should be from the bulk. Yeah.
Okay. That's the reason why the results.
Yeah, we can ignore the WRF-UPNB at this time from your comparison.
Okay. So this is a vertical cross section in the middle of the domain, and it looks similar. Let's just check it. No, this is just a qualitative comparison. It's difficult to tell whether it really looks similar or not. Okay, let's move on to the next slide. And this shows the time series of the cloud top height. As Wojtek already mentioned, OIRAG seems to be deeper than others. And WRF bulk seems to be too shallow. But except those two models, they are comparable.
Yeah, it almost looks like Shinichiro, like if you look at this around 6,000 seconds and a little bit earlier, the rate of growth seems to be kind of similar, but then other models kind of stop because of entrainment, I'm assuming, and my model is kind of keeps going. So yeah, so that's maybe the slope is slightly different, but it's not kind of completely off. Yeah, I don't know. I need to run. I had some ideas what might be going on, so I need to kind of go back to this and look into this more carefully.
Yes, the slope looks similar. Yeah. It's a little bit faster. The initiation of the cloud seems to be a little faster, but the slopes looks very similar to other models. So next is the time series of the total droplet number. It's again comparable, though I couldn't find enough amount of results. Or I only found four models submitted this data, but it's comparable. And this is a time series of total liquid water mass. Again, it looks comparable, except OIRAG. Now the vertical profile of the number concentration. And this looks very similar, comparable. All the models are within 500 plus minus 100 per cubic centimeters. So those dashed lines are guide for your eyes. And if we look at the vertical profile of the effective radius, then again, they agree well. However, if we look at the vertical profile of the standard deviation, droplet size distribution widths, it seems beam models predict wider droplet size distribution than particle-based models. So in this figure, tau beam and OIRAG beam and scale beam and WRF-LCM predict wider droplet size distribution, larger than 3 microns. But in particle-based models, CM1 LCM and OIRAG particle-based model and scale STM and UW-LCM, all of them are less than 3 microns. So this result is consistent, and this is what pointed out already in Wojtek's paper. Next is a vertical profile of liquid water content. As I already pointed out, in particle-based models, it seems like liquid water content can be larger than adiabatic limit. But as I already showed you, if we use enough number of super droplets, we can kind of eliminate this extreme cases. This happens only in the tail of the distribution. So now I check the numerical convergence of scale beam. So this is a number concentration of droplets, effective radius, and the radius of droplet size distribution for different number of beams. The first row is for 33 beams, 60 beams, and 100 beams. It was a surprise to me, but the result is very robust. Only from this, I have to say that the result is converged at 33 beams. But still, the droplet size distribution is wide. I mean, wider than all the particle-based models. So I thought that this could be due to the big fast beam. In this test, Yosuke Sato chose 3 microns for the fast beam. However, if we check the result of Eulag, this is a figure from Wojtek's paper. Again, I think, okay, the range is very different, but still 30 beams and 60 beams looks very similar. This shows the droplet size, radius of droplet size distribution. This looks very similar.
Shinichiro, we have a question from Adrian.
Yeah, please.
Hi there. So, yeah, I mean, this is really interesting. Can I just check, and I might have missed this, but so all these runs have precipitation on, don't they? Collision coalescence and all that stuff, or are these without collision coalescence?
All these result I showed you so far without collision coalescence.
Okay. Yeah, because so a long time ago, mainly because the KID A intercomparison is the most elongated intercomparison ever, I think. But I was doing some work with Ryo Onishi, and he ran his BIM model with, I can't remember, I think it was something like 60, 120, and 512 bins. And we, on the precip side, we did have to increase the number of bins dramatically to get convergence between the tau and his model. So, but yeah, if there's no precip on, yeah, I think this is okay. Yeah.
Thank you.
Okay.
Yeah, my interpretation of those results that you had previously, the previous screen, Shinichiro, with when you get, more models. I mean, yes, right here is that, the one way to think about this is that if you increase number of bins, then the bin resolution increases. And if you think about condensational growths, which is kind of like advection in the bin space. So if you have more bins, then the advection will be more accurate, and that should result in an improvement. Am I right? That would be kind of traditional expectation of why you would need to have more bins to do, let's say, to have smaller spreading, numerical spreading. But because this is clearly not the case, because your sigma is kind of very similar in all those from going from 33 to 100, I think another interpretation might be that this spreading actually comes not the advection in the radius space, but advection in the physical space, because you also move bins around, in the physical space, and then you advect them, and then you bring them up, to do condensation inside each grid box. And I think that's when this artificial spreading might be going on. So it's a combination. One thing that I kind of think Hugh Morrison did that he was arguing that actually the vertical resolution in the model is important. And of course, we haven't done that. So one suggestion would be to try the same tests 33, 60, and 100 bins with increased vertical resolution, only vertical, because of course vertical resolution gives you, that tells you how much you need to move droplet spectrum towards larger sizes because of the classical air expansion. That's what causes the air. So it's not necessarily horizontal resolution, but vertical resolution. So that's something that we may think about to kind of nail down where this numerical spreading is coming from. And I think Hugh has a paper on that. So we need to.
Actually, Hugh has his hands up. So Hugh, you're spotlighted. You can.
Oh, okay, very good. Let him speak.
You kind of stole my thunder. You basically said what I was.
Sorry about that.
So yeah, I mean, this is totally consistent with numerical spreading by vertical advection of the bin variables. And in fact, I would have been shocked if you didn't see that, because it's just a feature that I think is basically unavoidable. And this includes the spreading that you see right down near cloud base. This is totally consistent with just some really simple 1D tests that we did. And this is the paper that Wojtek referred to that we published in 2018. And we did a bunch of tests with different advection schemes, different bin numbers, different condensational growth methods. And the only thing that really seemed to address this was, like Wojtek said, basically increasing the vertical resolution. So I would definitely recommend trying to do a test like that. Of course, the downside of that is you're potentially changing the dynamics. I don't know if this would be possible in piggybacking to say, I know you had talked to Wojtek a little bit about piggybacking, going to higher resolution, interpolating the flow, something like that, to try and keep the dynamics the same. I don't know. There might be some discussion there.
Yes. Long time ago, I tried something like that, but it turned out to be not very interesting. But it was actually a little bit cumbersome how you want to do it. But that's certainly a possibility.
Well, you have to maintain non-divergence of the flow. I guess you have to be clever in how you're doing your interpolation. But something like that might be useful here, so you can keep the dynamics the same, but just increase the vertical resolution for the advection of the microphysics.
Yeah. We may think about that, but you can even do it offline. You don't have to do piggybacking. You can just save the flow and try to do it at higher resolution just by interpolating, I think, the flow and variable. But anyway, we can think about this. Yeah. Anyway,
just one last comment on that. I think you probably need to get down to pretty small vertical spacing. Obviously, it's going to depend on your particular vertical advection scheme, but in the tests we've done, you probably need to get down to something like 10 meters to really start to address this problem. So that's 5 times higher, I guess, than you're running now. So it's not a great solution to the problem, but at least it would maybe answer the question as to what's really causing the spreading.
Yeah, but the point is that you don't have to do it in 3, because if you do it, uniformly in 3 dimensions, that would be really a killer. 5 times to the power of 4 if you include the time step.
That's true. 5 times slower is a lot better than whatever 5 to the power of 4 slower is.
Yeah, exactly. But if you do just vertical, just in a test, that can be doable. Even if you have, that's only 5 times 5, 25. And you don't have to do it with large number of bins. You can do 33 bins. So that's already kind of that's doable. I would argue that's doable. Yeah.
All right, Adrian has his hand up one more time, and let's.
Yeah. Sorry. I hope you can all hear me. It's just to follow on from what Hugh just said. So if you take the vertical resolution down to 10 meters, then you're significantly changing the aspect ratio of your grid. So, I mean, Hugh, you commented on a change in the dynamics, but this is going to change the behavior of your subgrid modeling system unless you've got something that can adapt to that. So it might just totally change your simulation. That's just the way it is, really. But okay.
Well, this is, again, why it might be worth exploring that in a piggybacking kind of approach where you can really change the vertical grid for the microphysics, but basically not affect the dynamics.
Yeah, I think that sounds sensible, actually. Yeah.
All right, Shinichiro, go ahead, continue.
Okay. Thank you for your very informative and interesting comments. Yes, it really makes sense. I see. We have to do this test somehow very carefully. So let me move on. So this shows, this is something I already showed you, but yes, this is a comparison of 100 super droplets per cell and 1,000 super droplets per cell. And here I'd like to show that the width does not change very much if we compare, if we increase super droplets from 100 to 1,000. And next is the local droplet size distribution, categorized by the height and the AF, adiabatic fraction. The top row corresponds to the result of CM1 LCM, and the next one is from scale STM. And you can see that it looks very similar. It's very consistent. I'm happy to see this. Of course, it has to be, but yes, it looks very similar. So this corresponds to the height near the cloud base, and this goes up higher and higher, and Z equals to 2,400 to 2,700 corresponds to the middle of the cloud. Yes, it would be great if we have the same plot from some beam models. And WRF, Kyungok provided some result from WRF-UPNB, but unfortunately the range is too big for this comparison. It's from 1 micron to 1 millimeter, and it's
they use the log scale rather than linear scale. So if they just replot, that would be a really good comparison, in fact.
Yeah, I think so. So Kyungok, are you there? It would be great if you can plot it with this form, similar.
Yeah, I'll try that.
Yeah, please.
Okay.
Yeah, thank you. So maybe we can find some more insight from this comparison.
Yeah, Shinichiro, there's a question from the audience. Ishko, I think I spotlight you. You can unmute yourself and ask your question.
Yeah, hi Shima. So I was wondering about how did you or other people calculated the adiabatic fraction, because from tests that I did, so I've seen that the different methods of calculating the adiabatic fraction can have very large errors 2 kilometers above the cloud base. So we need to be careful when you're drawing conclusions using a adiabatic fraction for these kinds of regions for such a deep cloud.
Yeah. Thank you for your comment. Please.
So I just wanted to say that some of the sensitivity tests I've done are presented in a poster in this conference and also in a paper in ACP. So you can see it there.
Yeah.
Great.
I'll take a look at it. Thank you. Regarding the adiabatic fraction, yes, we noticed that it's very sensitive to how we calculate it. So I conducted some, careful test how to calculate it for this specific case, and I shared this information with all the participants. So I think hopefully they all calculate the adiabatic fraction following my formula. So it should be okay. But yes, we have to be careful about it. Thank you for your comment, and I'll check your poster. Thank you. So when I'm sharing my screen, I cannot see who is raising their hands or not. So can I move forward? Or should I?
Yes, I still see Hugh's hands up, but Hugh, if you don't have any question, you can lower your hand. Okay. Go ahead, Shinichiro.
And regarding local droplet size distribution, this is a result from Eulag, from Wojtek's paper. And I think he already showed this result, but it's good to compare this with this result, this line. So yes, near the cloud base, we have a unimodal distribution, but at the cloud top, and if the parcel experienced some dilution, we have this kind of tree model or multimodal droplet size distribution, very wide droplet size distribution width. And this is, I think, comparable to the result of CM1 LCM here and scale STM result here. Next is into comparison regarding the collision coalescence and precipitation. Now we have collision coalescence, Adrian. So okay, this result is from scale STM, and this from scale beam, and this from UW-LCM. Sorry, I didn't notice it, but I should have included the 500 super droplet case results here for UW-LCM. And we also have some data from WRF-UPNB. So for the polluted case, the control case, we do observe some amount of precipitation for scale STM, a lot of precipitation from scale beam. This is what kind of we can expect, because beam width is very bigger in scale beam compared to scale STM. But we do not observe this in WRF-UPNB, and in UW-LCM, they do not observe any rain precipitation for the polluted case. And for the middle case, 04 BG, kind of 400 ozone number concentration per grid cell, cubic centimeters. We have more precipitation in the scale STM and with some big scatter. And the result is not comparable to UW-LCM. They also observe some rain, but the amount is much smaller and the scatter is much smaller in UW-LCM. And if I remember correctly, this result is from 100 super droplet case, and if they increase it to 500, they observed much lower precipitation in their model. And this is more clean case. I observed much more precipitation as we expected for this case. And we also observed more precipitation in scale beam, and now it's comparable. In UW-LCM, we observed the precipitation increased, but still it's not comparable to scale STM or scale beam. That's it for the comparison of precipitation, I think. And finally, the computational cost. In short, I'd like to skip this slide, but the computational cost is comparable. It's in the same order, except UW-LCM, because they use GPGPU. WRF-UPNB, I think I changed the data just before this presentation based on Lulin's presentation, and this is still much more smaller than other models, but I think this is based on this case used 100 meter grid width, if I remember correctly. So
correct.
Okay. So that's it from me. So this is some list of what I think we need to do in the future. So in OIRAG WRF-UPNB, please check the configuration, and if possible, please resubmit your data. And we also need to check the numerical convergence regarding beams more carefully. And as Hugh and Wojtek pointed out, we have to consider the impact of particle grid resolution somehow. It's a little bit challenging, but interesting to assess it. And we also need to do some more analysis on precipitation. I definitely would like to see the result of CM1 LCM using the same aerosol number concentration with some ensembles, if possible, if you have some computational resources. Because the scale STM result and UW-LCM result are comparable but not consistent. And I also would like to see more result from beam models, but maybe we can expect that they predict more precipitation because the precise distribution width is wider than particle-based models. That's all from me. Any more comments, questions, discussions?
Yeah, we are a little bit late, so if there are no comments, we probably should kind of let people think about what we've been talking today. And remember that on Friday we have basically quite a bit of time allocated to some kind of discussion, socializing, this and that. I don't know how you can socialize on this platform, but maybe that's possible. And we also have to remember that there are posters, so the poster room has some posters. I'm not sure how you actually do it. Maybe Shinichiro, maybe you know how to do it and you can tell people how to do it.
Just go there, and there's some kind of place area for each posters. And if you go there, you can see the poster and communicate with the people in the area. So it might be much easier than how to say, hearing and saying some comments, questions in this lecture room. Yeah.
Yes, I think I can say something about socializing and poster viewing. So outside of these oral presentation room, there are many like a cafeteria area or sitting area that usually when you enter the area, there will be highlighted region. So everybody within that region can talk to and hear each person. And also in the poster room, each poster will cover quite a big area that once you step in, you can hear the conversation, and also your voice will be heard by everybody in that region. And also associated with each poster, there is a document, Google Doc, that you can leave your questions when the poster presenters is not there. And hopefully the presenters can also check that Google Doc to put your answers to those questions that they didn't get a chance to ask in person. So with that, also the breakout room works as like a poster or a cafeteria table. Everybody in that room can hear and talk to everybody. So that's a great way to have a bigger group conversation and socializing. So with that, we'll move forward to the poster viewing, and we'll resume tomorrow for the third day. Anything else from Sandeep or Harish, if you want to announce anything, and Tara? Okay. Great. All right, everybody, thank you for your time today and great discussion. Thanks, Shinichiro and Wei-Chak. It's a very good discussion today.
Thank you, Lulin. And tomorrow I will be sharing another YouTube link.
All right, thank you.
That everyone can watch. Everyone can distribute the link also, so that others who are not able to participate can watch.
Great.
Thank you.
Thank you very much.
Thank you, everybody, for participation. Thanks a lot. And thanks for the organizers.
Thank you very much. for your
All
participation.
right. See you in the poster room.
Thank you all.
Somehow kind of finalize this project to some papers.
Right. We should discuss that.